your seminar series. So, as you said already, my talk today will be basically covering some aspects of TLA plus. So I'll go through some of the works I did with some colleagues of mine to verify security properties in some systems, and also I would like to say a few things about our current work. But before moving forward and start discussing more about the TLA plus specific information, I'd like to quickly remind us how important it is to have systems that are free from flaws, errors, design errors that eventually, if they are present, could be identified by adversaries, and if they are successfully exploited, this may result in causing different problems. So here you can see I've listed very few, but I guess it's pretty straightforward to understand that if you have some security problems that eventually may lead in causing problems in providing your services to your customers, this may lead to having issues in the availability of the system. If the problem is too severe, an administrator might have to basically take the system down in order to fix the problem by applying some patch or whatever that would be. However, as you can see here, this actually may have quite a significant monetary cost. Other examples may fall under the category of legal implications. Imagine having a list of access control policies that you want to actually use in order to restrict access, of course, to the number of resources in your systems. If there are misconfigurations, then eventually, again, could be identified and exploited by adversaries, leaking to data breaches, leaking of data. And again, given we're aware of existing legal frameworks such as GDPR, this may actually result in for the company to pay a huge amount of money. And last but not least, another example I thought it might be interesting to list here is about causing some kind of damage to the reputation of the company itself. Again, if the systems that are deployed by the company are known to have severe security issues, this again may result in losing a lot of customers and eventually have an impact on the revenue of the company. Now, the question I would like to start asking here at this point is when exactly is the right timing for us to start thinking about security? And the thing that I'm trying to say here is that the sooner the better. And the techniques I'm actually using in my research are basically advocating that this is something we have to do from the early stages of designing the system. So this brings us, as you can see here, to a couple of interesting concepts such as security by design and formal verification. And I'm sure you are familiar with the concept of security by design. It's basically trying to integrate all the security requirements we want the system to support from the first from the early stages of designing the system, and not to consider them much later down the line as an afterthought, which is unfortunately something that happens if a company like an SME doesn't have the capacity to do that. Just one thing, just to make sure I'm not to misunderstand what I'm saying here, it's also critical to have other countermeasures, security controls in place during the operational phase of the system, but this is not what I'm covering today. It's more about the design phase of the system and try to introduce all these security requirements during its development. And also formal verification, I hope you're all familiar with. It's about using mathematical tools, methods in order to provide strong guarantees about their correctness, and not least about making sure that it works up to the security specifications requirements. Some things about the benefits of employing formal verification in the development of systems. As you can see here, formal verification allows us to identify and correct errors early in the conceptual phase of a system. Okay, And by doing that, it helps us also to ensure that complex systems, which is the case for today's systems, to have this kind of very increased complexity, to behave as anticipated. So this is really important, to have a system that operates to the specifications. And basically, by identifying promptly vulnerabilities or flaw in the design phase, we can end up enhancing the overall security of the final product, of the final system, and sometimes also ensure its robustness as well. So this brings us to the main objectives of this presentation. So as I said already, I will talk about the use of TLA plus as a formal specification language to specify and automatically verify certain type of properties, and then also talk a bit about interactive theory improving at the very end. So I'll just do this brief introduction, then go through a system we designed and verified before, a usage control system, and then explain you some current ideas we have about automating the generation of TLA plus properties from a natural language. And last but not least, say a few things about some recent works we did on extending the existing functionality of the proof manager for the TLA plus ecosystem. So what is TLA? A few things, since as Vasily said, he didn't he doesn't know a lot of this specification language. So TLA plus is a formal specification language that has been invented by Leslie Lamport. It's particularly well suited for specifying and reasoning about complex algorithms and distributed systems. And it is used also for creating, of course, high-level models of systems, which can include concurrent processes, of course, and any other type of advanced capabilities you want to introduce in there. For instance, another example could be have some kind of fault tolerance mechanism you want to specify and verify. Another thing that I would say that TLA Plus excels in is at modeling systems where the components operate in an asynchronous manner. So this means that the exact timing of actions is not very critical for the specification of the system. And of course, having the system specification, as we will see soon, we can start defining properties of interest to verify them. Something that is also, I think, quite interesting to say here is that it is supported by quite a few major companies, such as Microsoft, Amazon Web Services, and Oracle. And there is also the TLA Plus Foundation. So following this link, you can get more information about the foundation itself as well. So I think at this point it might be interesting, since I've talked at very high level what TLA Plus is about, to give a bit more information, just to make it clear how we can start using it in order to specify the behavior of systems. TLA Plus is based on set theory, and it is an untyped language. And we have a set of constructs we can use in order to start defining this state machine that actually has describes the behavior of our system. And we can use, as you can see here, sets, functions, records, sequences, tuples, and so on and so forth. And of course, we do have variables that we use them in order to represent the different system states. Eventually, what we want to achieve at this point is to define this state machine that will have eventually in it the behavior of the system we want to model. And in order to do that, these are the main steps we usually follow. So this is a short example just to give you a bit of better understanding how we can start modeling systems using the language itself. So we can start defining a number of predicates. Here you can see that we have to define an initial condition the system can be in. So the init predicate here defines as x equals to 0. So the variable x is an integer in this example. And then we have to start thinking about how we can build the next stage the system can be in. And this is what this next predicate here is expressing, which is defined as this if statement, which is very close to what we know from other programming language. So if the value of x is less than 3, then x prime equals x plus 1, with x prime being a TLA plus way of saying that the value of this would be the value of x in the next state. So if the condition is true, so the x prime will be evaluated. If this is evaluated into false, then the value of x will remain unchanged. And by having this kind of predicates and actions, we can basically start defining the overall system specification, which looks like this spec here at the very bottom of the slides. So the spec here is defined as this initial condition and having the conjunction with this formula here. And this is how we can define the system behavior, the state machines that will include all the different states the systems can be in. Now, having the system specification is great, but what is that we can do next? Of course, we define the specification of a system so that in a later point we can start defining properties we want to verify and check for correctness. Generally speaking, there are a couple of two different type of properties we can verify with TLA+. So safety and liveness is what I'm listing here. So safety is about checking that bad things don't happen. Okay, and think of that as being some kind of invariant for the system. And here's a few examples to see how this invariance may look like and what is that we can check. For instance, the first example is checking type correctness. So this square brackets creating this box is the always temporal operator. So this means that always x should be in the range of 0 to 3. So it's not possible for x to get any value out of this closed set of integer numbers. Why this is important to have and check in a TLA plus specification? If you remember, I said that TLA plus is an untyped language, so it does make sense to make sure that whenever you have variables, the values in them actually range over the sets you want to for these variables to range. Other things that we can do is try to detect that the system is in a specific state. So here you can see that always if x equals 1, x will be greater than 0. Other examples here are how we can check if a system can end up in a state where the value of a variable is not changing over time. So it stays as an invariant. So this is how such specification would look like. So always x equals 3 implies always x remains 3. And this is what you can see here on the right-hand side with the graph. Now, apart from safety properties, we can also verify liveness properties, which are about good things always do happen. We do need liveness properties because systems do evolve over time. So it's not only about invariants we're concerned, but also about things that eventually can happen. And this is basically the example I'm giving here, using something that can be detected eventually in the system, meaning that if x equals 0, which is the first state in our graph, eventually x will actually take the value of 3. And this is what we can change very simply by using this kind of temporal formulas. A few things about the existing ecosystem. So we do have the TLA plus language, which is the main mathematical language we use to specify systems. On top of that, we have also Pascal, which is a front end to TLA plus. It's something that people use, I guess, mainly if they want to verify algorithms. And we do have a couple of different IDs to start using the language itself. We do have the TLA plus toolbox, and also there is an extension for Visual Studio Code that someone can use. It comes with a couple of model checkers. For now, TLC is the main model checker that is supported by Toolbox, which is an explicit state model checker. Here, I would guess that this is a more appropriate model checker for checking software-based systems. And we do have also Appalachee, which is a symbolic model checker for TLA+. Gives you to symbolically verify safety properties. And last but not least, apart from model checkers, we do have also a proof system in place that we can use in order to define our own theorems and try to provide more general solutions, which is a requirement for some problems. So let's move ahead with this kind of motivating example, just to make it more clear how we can start using this to start modeling a bit more complex systems. So the motivation here is that at some point we have to design and verify a usage control system. And the question there was how basically you can do that, how you can achieve that, and why it is important. It is important, as you can see, because having a system specification of that usage control model, it would give us the opportunity to verify that the model itself was operating correctly. And furthermore, it would be really great to have such a thing because we could use it to make sure that the policies that were enforced were enforced in a correct manner. And this is important, as I said before, since it can help us to avoid specific type of security breaches or causing privilege escalation and things like that. So I will not get into the details. There is the paper I'm citing at the bottom of the slide. So this is just to understand how the main elements of that use-based control model called UseCon looks like. So you can see that you have subjects. So subjects request the execution of an operation on object entities. You have objects. Objects in access control are usually passive entities of the system. You have actions, which are usually complex operations in this particular model that may impose restrictions from a set of attributes that are present there. We have also the concept of use, a set of uses, which are security-related semantics of a usage by using a combination of subject, objects, and actions. And this is the states a use can be in. So this is what we designed, and we wanted to make sure that whenever something was actually starting in our system, it would have been always initialized with the init state, and then based on specific actions, we could only move to the right states. And this is what we were trying to model and make sure that everything was operating as anticipated. In order to start doing that, of course, you have to start using the concepts that are offered by the language itself. I do provide links to the specification, so you can download that from GitHub and try to test and see how things work if you like. So in order for us to do that, we had to define a number of variables, a number of constants, and start defining the set that would actually make sense to specify correctly the anticipated behavior of the UseCon model. And eventually, we managed to successfully model the transition systems of the UseCon. You can see here that this is basically a subset of the transition system I showed just a couple of slides before. And the reason for that is because the UseCon model by design had two different authorization models. the pre-authorization model and the ongoing authorization model. So just for giving you an example, I'm just quickly covering some things about how this pre-authorization model, which is what you can see here, could be modeled. So as we saw through the simple example I talked at the beginning, you have to have an initial condition, and this initial condition is defined as follows in for the use code model. Basically, we were creating we were initializing all the UIDs having an init state, and then we were defining the next state the transition system could be in, which could be request, pre-evaluate, or complete. So you can very easily do that by just using this disjunction. And by having the initial state, initial condition of the state of the system, and something that describes every next state the system can be in, we have eventually our specification, which is expressed in a very similar manner as the example we have before. Keep in mind that when you want to verify liveness properties, as I will go through a bit later, you have to make sure that you're actually using also as a property their weak fairness in order to make sure that eventually all states will be visited. Otherwise, due to the stuttering mechanism, this may not be possible. And this again is an example of how these different actions that can move you from one state to another may look like. Again, I will not get into the details. This is just an example to show you how such a specification may look like, and try to demonstrate the high level of expressiveness you have with TLA plus. You can see here that under this pre-evaluate predicate, we actually introduced also the different policies we would like to evaluate, and in case the evaluation becomes true, then we would redirect the system to the correct state it should be in. So if this is true, then it would be activated. Otherwise, if the policy evaluates into something that is false, access would have been denied. And this is an indirect way for us not only to verify the internals of the model, but also how it evaluates different policies. And this is basically a simple example to show you even how such a policy may look like, or what is that we can actually describe in that specific example. So as you can see here, a policy will define this high-level requirement that actually provides further information how a specific resource of a system can be accessed. And in this example here, we introduced AID as an action in order to implement the following policy. So the idea here is that whenever you have a subject that requests to get access to a specific document, to view that, that specific subject would have to agree before on a non-disclosure agreement. So it's quite complex as a concept, but it's something that can be expressed and verified and supported both by the model and the language as well. So this is how such a policy we already have in the specification of the model looks like. I will not go into the details. I'll just describe this at a high level. So the rationale here behind this policy is that if we have the subject, as I was saying before, that requests to perform an action on an object, the requested action is permitted if and only if one of these two following things are happening. So the first is that the action is the non-disclosure agreement itself. So in the future, this specific subject could actually use the object, view the document specifically, Or if it's not this the case, then the other case is that if the action wants to view the document, the same subject should have already completed a non-disclosure agreement action in the past on the same object. So you see that there is quite a complexity there supported by this security requirement. Nevertheless, we can quite easily express this kind of complexity using TLA plus and verify if this is correct or not. And this brings us to the different type of properties. As I said before, what is having a specification is great, but what's next? Eventually, you want to start thinking about things that make sense for you to formally verify and make sure that are correct. And therefore, your system is secure. We did check quite a few different properties. The first family of properties, as you can see here, are this set of safety properties that can be expressed in TLA plus like this. So always for all use in the set of use, when the state of a U is completed, this implies that we'll never take any of these actions. And this is just something we wanted to make sure that operates, works correct. And this is how we defined all these different properties and formally verified them. And here you can see that we did this for both models supported by UseCon, so both the pre and the ongoing one. And in a similar manner, we wanted to see that eventually you can move from one state to another. Otherwise, if you can't move from one state to another, then it doesn't make sense for the system to exist. And this is why we defined and verified a number of liveness properties similar to the safety ones. And these are some performance metrics. I won't get into the details. I'll just say a few things about how far we managed to go. So here you can see that we managed to verify up to 10 uses for the UseCon system. And when we tried to increase that, because of the state explosion problem, we ended up spending lots of time trying to verify the properties. So it was taking a lot of time. Meaning that we had to stop sometimes the execution of the model checker, which is fair enough, to be honest. So the claim there for us was to refer to the small scope hypothesis that states that analyzing small system instances is sufficient in practice, since a high proportion of bugs can be found eventually by verifying a system for all inputs within some scope, like the one we did. However, if we would like to provide strong security guarantees for any number of uses, we would have to basically move away from the model checking technique and try to employ the theory improvers, okay, which is of course supported in the ecosystem we have. However, we didn't try it, at least for now. So this kind of lead us now to something kind of different. I want to discuss about the system properties more specifically. We did see with the examples how you can specify the behavior of the systems. However, when it came to the properties, I just provided you with the properties. And what we are currently trying to think about is how we can basically improve this process. Since defining correct properties for verification, it's not an easy task, to be honest. First of all, it requires a very deep understanding of the system. This is something that you can't really avoid. However, the thing we were trying to improve with what I'm going to shortly to talk about is how to automatically generate properties and making sure that these are expressed correctly in the selected language, specification language. So in order for us to do that, we rely a lot on things that exist already. So the big idea basically is what you see here at the bottom. And I'll quickly reach to that point. So the idea we have is basically to utilize FRET, which is this formal requirements elicitation framework that has been developed by NASA, and basically use the natural language that they defined, which is called FRETIS, in order to eventually describe using natural language properties that can be converted into TLA plus properties. Okay, so that's the overall idea. And before saying more about that, I think it's important to understand what are the main fields that this Freitas language is able to support. So this is again some information for the FRET framework. So it's work that done by NASA and not by us. So you can see here that there are quite a few different fields. So we have the scope, which specifies the interval, which is relative to when a specific mode holds. We have conditions that are Boolean expressions that can trigger the need for a response within the specified scope, of course. The timing field that specifies when the response is expected. Components that specifies the component that the requirement applies to. Sorry. The sol keyword, the sal keyword, and of course the response field, which is expressed as satisfy the response, and this response is a non-temporal Boolean expression at this point. The fields with the asterisks are compulsory, and the ones without a star, without an asterisk, are not required every time you specify something. So what we're currently looking at is basically use what is produced out of the FRET framework and try to convert it into equivalent TLA plus properties. Now, there are, of course, implications here. So we always have to make sure that to check for syntactic and semantic equivalence between the code that has been produced by FRET in SMV and how this may look like in TLA plus. Of course, things such as operators supporting conjunction, disjunction, negation, implications are there, and we can use at this point temporal operators such as the all with and the eventually, as explained before. Just a quick note on things that we kind of currently support. There is no we can't really support anything under the field of scope. When it comes to conditions, we can leave it again as empty, blank, or we can use the whenever keyword. And when it comes to the timing field, we can use, as already said, always, eventually. However, we can use also never and immediately. And I'll go through some examples just to make it clear what this means and why we have this kind of restrictions. So this is eventually how the idea looks like. So using Pretis, you can start defining using natural language, following, of course, the supported fields, the properties you want to specify later on in TLA plus, and these are some examples. So the system shall always satisfy x greater or equal to 0 and x less or equal to 3, and you can generate equivalent properties like the one at the bottom. Another example is requirement 2. The system shall always satisfy if x equals 3, then globally x should be equal to 3. And in a similar manner, we can generate this kind of properties. There are more examples that might make a sense to go through. So here you can see another example that is using the eventuality. So R3 is about having a system that shall eventually satisfy x equals 3, and this is what you can produce, and you can just put it in TLA plus and verify it as a property. And of course, another example here, the system shall always satisfy if x equals 0, then in the future x will be equals to 3. Now, some of these examples might actually appear to be quite trivial or easy or straightforward. That's true. But imagine that when you have a really large system, specification of properties could be actually much more complicated. You might require even to have some kind of composition across all these properties. So it does make sense to have a way to describe the properties using a natural language and get something that avoids all this ambiguity. And this is, again, something slightly different, also trying to utilize a condition here, as you can see. So whenever x equals to 1, the system shall eventually satisfy globally x greater to 0. So again, by collecting what's been generated by Fred in SMV, then we can actually look how we can map it to equivalent TLA plus properties and verify them in the system. However, there are some limitations in this approach. So one of these limitations is stemming from our reliance on what's been created as an output from the Fred framework. So the problem there is that there are specific operators supported by the linear temporal logic in Fred. However, it's not the case for TLA plus. So you can see here that I'm saying that TLA plus formula are invariant under stuttering, meaning that these are insensitive to adding or removing a finite number of stuttering steps in there. And therefore, it's not possible to directly express operators such as x, which is next in the linear temporal logic, since you can have many different states where stuttering can actually keep on happening. And also another thing that we're looking at, and it's not currently supported, is how to introduce quantifiers over sets. Since if you remember, if you go back to the example I had for the usage control system, you would see that we have a quantifier over a set. It was the set of IDs, UIDs there. However, this is not something that is supported by the linear temporal logic, at least the same way as in TLA plus. So that's something that we can also try to look in the future. So this again brings us to the last part of this presentation, to talk also about another recent work we did. So so far you may have seen that we've been using TLA plus to verify discrete systems, which is fair enough. However, we were trying to investigate how we could potentially extend the existing ecosystem of TLA plus in order to start verifying systems that might exhibit some kind of continuous behavior. I have an example just right after that, so I provide more information. Now, the good thing is that TLA plus already, as you can see here, supports allows specifications to involve reals. And the thing that was missing was the tools that were able to verify these real arithmetic proofs. And what we did was basically to introduce this in the existing TLA proof manager. And we could actually, by the work that we described in the paper, we can create now SMT-lib code that can be sent over to Z3 as a solver in order to provide us with a response if it is satisfiable or not or unknown. So few more information about how what are the changes that we introduce. So there are a couple of things that are changed. So we had to update the existing type inference algorithm, and in order to do that, we introduced some additional typing rules to support reals. And another thing we updated, it has to do with the untyped encoding supported by the version at least of the TLA proof manager we changed. The reason why someone might actually try to move away from typing rules and try to use the untyped encodings is because you might want to just delegate the type inference of the variables to the solver itself, and this is what the untyped encodings are able to achieve. And again, this required to introduce some axioms for reals in there. Overall, this is again not all the components of the proof system. It's just a partial representation of the proof system, and you can see here that we have a TLA plus specification that can be used as an input to the proof manager. It goes through all these different processes that have to be done in order to generate the proof obligations. And you can see here, when it comes to translating that into SMT-lib code, we have applied changes in the type inference algorithm, as I said before, which again requires some changes in the syntactic rewriting when it comes to producing the SMT-lib code. And having that SMT-lib file, it's forwarded basically by the proof system itself. When you call the right backend, example, we use Z3 as I said here, and we can get a result. Now, this might actually sound very high level and clear. So this is why I have an example, just to make it a bit more clear how a continuous behavior might look like and how we can basically use that. So this is an example of a discrete-time dynamic system we have in the paper. So you can see here that we have a couple of variables that range over the domain of real numbers. And these two differential equations basically could provide, these two equations could actually provide the dynamics of a system. So they describe how this system can evolve over time. We suppose that the system can be initialized from any state that satisfies this inequality. So x squared plus y squared less or equal to 1. And the next step is basically to start thinking about what is that we want to verify. And this is the safety property. And the safety property here is that this absolute that the absolute value of the x variable should never exceed 1. Now, here you can see that if we actually try to plot this, we can get something like that. So using some numerical analysis, we can see that this is how the system looks like over time, and it might converge very close to 0. However, this is just a numerical representation of the problem. It doesn't actually provide any proof, any guarantees about the correctness. Okay. So we have basically to do something different. And what we have the capability now is to define proofs. So in order for us to prove this, we consider this inequality here to be our candidate inductive invariant. As you can see, the initial state is quite trivial to prove. What remains to show is these two statements, that no unsafe state satisfies this inequality, and that this inequality is also an inductive invariant. And we explain what is that has to be done, basically, how to show this. And I'll try to very quickly summarize, since we're kind of running out of time. So knowing basically what is that we have to verify, of course, we have again to specify how the system looks like, and this is how in TLA plus this looks. So in a very similar way, we have the init predicate that initializes the values of x and y to 0 and 1 respectively, and we have the next action that expresses how these variables may change over time. And of course, we know already that this is sufficient to specify the overall specification of the system to include the behaviors. You can download this proof and specification from GitHub, so I have the link here. I'm happy to share the slides after the talk. And having that, we have basically to start using now the interactive theory improver that is present in the TLA plus ecosystem. And this is how we can define our safety property, the inductive invariant, and then we have to start building our theorems. Keep in mind that in TLA plus we use hierarchical proofs. And hierarchical proofs is a way of structuring proofs in hierarchical manner, of course, which makes things a bit easier to understand and manage, hopefully. So in a TLA plus proof, there is, of course, a current obligation that has to be proved. The obligation may contain some context of known facts, definitions, declarations, and of course a goal. And the obligation claims that the goal is logically entailed by the context. And this obligation then is sent to the backend. In our case here, you can see that this is Z3, and we can basically get a response back from the SMT solver. This is just a small part of the theorem. There is much more, but I think it's out of scope to go into the details of that. You can have a look and you can experiment with it if you want. And if you have any questions, feel free to contact me. So just to quickly summarize, I think that I kind of demonstrated that TLA plus is quite highly expressive language that can be used to specify and verify modern systems that may have quite significant complexity in them, and also went through some of the capabilities we are currently working on extracting the existing TLA plus ecosystem, which is mainly about automated property specification and also being able to verify continuous behaviors using the existing tools nowadays. And that will be all. Thank you very much for your attention, and I'm happy to go through questions if we have time.
Thank you, Antonios. Let me stop the recording.